Okay, I'm going to go over the last couple of questions from the review for exam 3 since we didn't get all the way through it in class. So I'm going to go over number 8 and number 9. So let me start with taking a look at it. Now, in one of the classes, we actually got through the first part of this problem. Let me grab a pen. All right, so we had talked through this bit before, but for the other class, I don't think we even got through anything past part A. But we're going to identify all these numbers and put them into the right places here. So it's actually asking us to find the future value. So we're going to figure out what the output is after 10 years. So that's A of 10. The principal investment is $3,000. 1 plus R. The rate, if it's 5%, we have to convert that to a decimal. So 0.05 divided by. How many times per year are we doing this? Monthly means there's going to be 12 computations to the 12 times 10 years. All right, and if we're careful, we can put all that directly into our calculator here. And we did this before, so I'll just go ahead, 3,000, just for practice. So if you're trying to do this like a practice test, make sure you can do this. 0.05 divided by 12. I'm just using divide as a slash, and then to the power of, it's this button right here. So to the power of 12 times 10. I want to tell the calculator that both of those numbers are up there in the exponent, so I'm going to use parentheses for this piece right here. Hit the answer. And I'm going to get 4941. I think we're rounding to the nearest cent. So that's 2 decimal places. So 0.028 will round up to 0.03. So 4941.03 is how much a $3,000 investment will grow to at the end of 10 years, compounded at 5% monthly. That's what it grows to, almost $5,000. Okay, now it says what would the initial investment be in order to have a future value? So we're using the same model but slightly different values. So we want a final value of $20,000. So we want this number over here to be 20,000. And then they give us a different time value, 20 years. So T is 20. 6%, which would be R equals 0.06, compounded monthly, which still tells us N is 12. So R is 0.06. 20 years means T is 20. So this one we actually don't have to solve for anything in the exponent either. So the outcome is 20,000, and we want to know what goes here. What principal investment, how much do we need to start with so that at the end of this time this calculation will grow this dollar amount into this dollar amount. Okay, so even though it looks like it's all complicated and everything, we're just solving for this piece right here, and it's just P times all that. So if we can just evaluate all that, we're going to divide that under the 20,000, and that'll be our answer. I'm going to do this in 2 steps, and I'm going to let the calculator hold on to the answer. Again, we did this in one of our classes, but I don't remember which one, so we're going to do it together. So I'm going to do just this piece. I need to put parentheses around that, sorry. 1 plus 0.06 divided by 12. Raise all of that to the 240, or if I'm going to do them times individually, 12 times 20. Close my parentheses. So that part is 3.3102, blah, blah, blah. I'm not going to try to write all that down over here. I'm just going to use the calculator's storage button down here over the negative key under the 3 key. It has ANS for previous answer. So if I want to take this and use it in the next calculation, I can just type 20,000 divided by and hit that answer key, and that'll give that the most accurate value. Okay. So I'm going to do, on the next line, I'm going to do 20,000. I'm going to divide it by the previous answer. So second answer, like that. Hit the answer key, and that's going to give me 6041 point. We have to round it to the nearest penny, so 9.2. That first 2 is the pennies, and the next one after that is a 2, which means the 2 stays. 1.92. So 0.92. So that is how much money we will have in the account after 20 years, 6% compounded monthly. And that's also, since that's not how much we'll have, I misspoke there. That's how much we have to start with here in order to grow it to $20,000 at the end of this time. So that would be your starting amount. You have to have about $6,000 to grow it to $20,000 under those conditions. 6% compounded monthly over 20 years. Okay, so that's number 8. And then the last one that I put on here does have a little bit of solving we have to do with using logarithms and stuff. All right, so let's see what, this is the model that we're going to use, or the formula we're going to use. We'll plug in our specific numbers and it will become a model for this situation. So a person bought a car for $25,000. After 3 years, the car was worth $15,750. Assume that the price is decreasing according to a continuous exponential decay model. So this is calculating the price or the value, I guess, of the car after a certain amount of time. So this means that this amount, the starting amount, is actually going to be a higher amount. It's going to be what the value of the car started with. And let's go ahead and figure out what we're going to have to do to solve for k. Let's look at this thing and notice where the k is. It is up in the exponent as well. So we're going to have to take this equation and solve it for k in the very similar ways that we solve for t, because t is also up in the exponent. So if either one of these is what we're solving for, we're going to have to set it equal to a number and work it out and use a logarithm somewhere. So let's figure out what everything is. So the final amount after 3 years, so 3 is going to be my t value. The value at 3 years would be this number, so that's what goes over here. So that would be like our a of 3. That would be the outcome. Okay, and then we're trying to find the rate that was used here. So, all right, so let's put it all into our formula. So a of t, that's the amount after 3 years. That's going to be the lower amount because it's decreasing in value. The starting amount over here is the price of the car at the beginning of this time period, 25,000. E is a constant. That's always going to just stay E. It's at 2.71828 out of our calculator. Negative k is what I do not know. And then the t value, how long did it take to get from this amount down to that amount? 3 years. So we'll put a 3 there. Okay, so you solve for the rate in the same way that you would solve for the time. You fill one of them in and you find the other one. They're both in the same exact place in the equation, so we'll do the same exact steps to untangle it and get to that value. All right, so the first thing we'll do is take everything that's not part of that base and exponent and move it to the other side. And since that 25,000 is a multiplier, we're going to divide by 25,000. Let me see if this gives us something pretty as a decimal, or do I need to keep the whole fraction? So 15,750 divided by 25,000.63. Okay, that's a nice, easy decimal. So I'm just going to go ahead and use 0.63 instead of writing the fraction version of this. Now the 25,000 is gone over here, so I just have e to the negative k times 3, so I'm just going to call that negative 3k. All right, so that's our starting maneuver on any of these exponential equations, is to remove any other numbers that are not part of the base and exponent piece. So usually it's division like this. And then on the next step, this is where we apply a natural logarithm to both sides. That's going to be convenient over here because the natural logarithm won't cancel out the e. So I'm going to apply a natural logarithm on both sides. You write it in front of whatever you're taking the logarithm on or of. And in this case, since it is base e, we don't have to use the power rule for the next step to simplify it. We can just cancel the natural log and the base of e. So that means on the next part of our problem, we'd have the natural log of that 0.63 equals, the e and the natural log are gone, it's just negative 3k. Well, we're solving for k, so the last step would be to divide both sides by negative 3. Then we can go back to our calculator. Now it says round it to 3 decimal places. It has a logarithm in it, so it's not going to be, an exact answer. So let's put this into the calculator. So we're going to do natural log of 0.63. We're going to divide that by negative 3. Okay. That gives us 0.1540. It said round to 3 decimal places, so fortunately that's easy because the 4 is followed by 0, so 0.154. So k by itself is about 0.154. The interpretation of this could be that the car is losing about 15% of its value each year. So we're going to say 0.154 if we're rounding to 3 decimals. Okay, a lot of times we do this when we're really trying to do modeling, because a lot of times we don't know what we know. We assume that it's exponential growth or exponential depreciation like this, because that is how car values work. They usually decline according to exponential models. They lose a lot of value at the beginning, and then they kind of flatten out and don't lose as much as the car gets older. So generally all you need is the starting amount, the final amount, and the amount of years that it took to go between those two. And if you have those 3 pieces of information, you can plug it into this model and come up with the decay rate or the depreciation rate. Once I know the depreciation rate, I can write a new model. So here's my model I'm going to write now to answer the next question. I can write a model that just looks like a regular function with only t and a of t not filled in, and then we can make estimates or predictions using that. So in general, the amount will be calculated by, we still have all this, the 25,000 is my initial value, e to the negative k, which I now know is 0.154. In this case, I want to leave the t in there because I want to make it look like a regular function where I just have a of t, the output, and I have t over here, the input, and everything else is filled in. So once I have a model written down for this specific situation up here, I can either figure out what the value is going to be after a certain number of years by plugging in the years here and just working that out, or I can answer other questions about how long will it take for it to equal a certain target value that we put here, and then we solve it. All right, so let's see what answer B is, or question B is. Find the car's value after 5 years to the nearest dollar. So they're giving us a time period, so we're going to put that here and basically calculate a of 5 on our calculators. So this is what we're going to put into our calculator. 4 times 5, like that. Okay, so let's go back to the calculator. Okay, I'm going to type this expression in. So 25,000 times e to the power of, and to remind you, e to the x is above the ln, the natural log button. So if you want to put an exponent on e, you can hit second ln and it will pop up the e to the power of, and you just type in your exponent. And we're looking for an exponent that has this product, negative 0.154 times the year 5. Okay. So there's this is the exponent on the e. Make sure and wrap it up in a set of parentheses, and then let's see what we get. Okay, according to this, that's how much it's going to be worth in 5 years, which makes sense. In 3 years, it was worth 15,000 and something. So a few years later, it's worth a bit less, 11,000 something. Let's round this to the nearest dollar, it says. So 11 and 57. The nearest dollar is the nearest ones place in front of the decimal. So we have to round all the values up to the decimal, and the 5 is not going to round up because it's followed by 3. So 11,575. So that's how much it's going to be worth to the nearest dollar in 5 years. All right, and then the last question is setting up an equation. Find out how many years it will take, so that means find t, for the car to be worth $10,000. So the value of the car at different points in time is over here. It always starts with the initial value of the car is 25,000, but at different points in time it's going to have different values, and you put those other values over here. So we want to know if the outcome or the value is $10,000 on an original car's value that was 25,000. How many years approximately will that take to depreciate to $10,000? And we can round it to the nearest tenth. We're going to have to round because it's going to have a logarithm in it. All right, so let's go and we're going to do pretty much the same steps that we did just up here to find k, except this time we know k and we're trying to find t, but they're both in the same part of the problem, so we'll do the same thing. We're going to divide, take a logarithm, and then divide again. All right, so the first thing is to divide that 25,000 to the other side because it's not part of the base and exponent. I just put a box around the base and exponent to remind us. And I think 10 out of 25 also, or 10,000 out of 25,000 also works out to a nice even decimal 0.4. So I'm going to use 0.4 instead of the decimal, instead of the fraction. and that's going to equal e to the negative 0.154t. Once we've done this, we're going to apply a natural logarithm on both sides so that we can cancel that e, like that. And we're just going to get on the right-hand side what was in the exponent. Now that's all there is. So we just write that as an expression with the product of the decimal times t equals this logarithm on the other side. And all we're trying to do is solve for t. So we've gone from t being up in the exponent on e to some stuff canceling out to where it's just t times a number. So to solve that finally on our last step to get the t by itself, we have to divide that decimal to the other side. So t is approximately, because this is the exact answer, natural log divided by negative 0.154. So let's see what the value of that would be a little more understandable. So 0.4, we're going to divide that by negative 0.154 equals 5.94999, so about almost 6 years. So it's 5.9499, but it said round to the nearest tenth. The tenth is the first place after the decimal, which is at 9. It is followed by 4, which isn't big enough to bump up the 9. So we will say 5.9 years. Okay. So that it kind of finishes up how to do the last couple of problems on the review. The ones here where we have to find out how many years it takes, or if we have to find a depreciation rate, those are the kinds of problems where we will have to do a logarithm somewhere, and there will be a logarithm in the final computation to get your answer. So down here there was a logarithm in the final answer. If you look at some of the other ones, we have done this one in class, but this is another one. After how many years will the population reach 3.3 million? So you set it equal to the 3.3. That's a decimal point times t. So this is another one where we're going to have to divide, then we'll take a natural logarithm and cancel the e over here, then we'll divide that decimal again. So this is another one that has the same procedure as those other two word problems. All three of these that are starred, number 7c, number 9a, and number 9c, all of those have the same exact steps for getting things solved. And then A and B, or not other ones where if it's not if the base isn't e, we did this in class. If the base isn't e, then when you do your natural log on both sides, you're going to have to bring the exponent out in front. So we'll have natural log 5 to the 2x, natural log 300. If the base isn't e, when you get to this step, you bring it out in front. And then what's going to happen is you'll divide, but you're going to divide probably a logarithm and a number to the other side. X equals this fraction. So that's what you'd have to put in your calculator. But the only difference between this one and all the ones with base e that we were working on, a lot of them were base e, is when you do the logarithm on something that has a base of e, the logarithm and the e will just cancel out on that side of the equation. If you do the logarithm on an expression where the base is not e, we can still simplify it and solve, but we'll have an extra step where we bring that exponent out and write it in front of the logarithm. The logarithm won't go away, but the exponent will be written in front as a multiplier. And then to finish it, we will divide both sides by whatever else is in there except for the x. So there'll be, you'll divide by another logarithm and possibly another number as well. Okay, so that gets us through number 8 and 9. The rest of the review. So if you have other questions, shoot me an email. I'll be happy to answer your questions as they come up. So good luck studying, and we'll see you guys all on Wednesday. We do not have class on Monday to take our exam. So be on time so you have plenty of opportunities to ask questions and finish your problems and check your work and all that stuff. Okay, let me stop this so I can get it uploaded.